Okay, megafaunal extinction. Video number 2, I think, isn't it? This is the second one on megafaunal extinction. And we ended the last one asking why doesn't the model lead to extinction and how could we adapt it? And we're now going to answer those questions. So the model doesn't lead to extinction because, and I basically told you this already here, with the diagram before. When the megafauna start to become very scarce, then the humans have got nothing to eat, so the human numbers fall, and therefore the pressure on the megafauna relieves, is diminished, and the numbers go up again. Then the human numbers go up, pushing the megafaunal numbers down again, and so on. Okay. But basically, because the humans are totally dependent on the megafauna, they will never go extinct, because if they start getting extinct, the humans all die. Okay, what could change that conclusion? Well, one thing that could change it is if there are the famous tipping points. Okay. Tipping points, beloved of environmentalists and all those who, or many of those who are pushing for tougher environmental policy. Why? Well, and what might a tipping point look like in this megafauna model? Well, I never showed you this, but if you've done the biological resources, you'll know this. The logistic function for the growth part of the megafauna looks like this, where this is, let me see, this is n, the number or the mass of megafauna, whatever, and this is n t plus 1 minus nt. So this would be nt then. So what's this saying? Here we're at, what did I call that? N star. So when we're at n star, then this is 0, yeah? And if n is 0, then this is also 0. But if n is in between, then we have a maximized growth rate. It turns out it's in the middle. When n is n star over 2, that's when you have the highest amount of growth. Okay. But the steepest point is here at the start. Okay. But maybe it doesn't look like this. Maybe, remember we talked about these megafauna being hard to find, which is what we're basically assuming by setting up this model, or this equation. What if they have trouble finding each other? Okay. What if they have trouble finding each other? So that if there's only a few of them, they can't find anyone to be their mate. Okay. What's going to happen then? Then we would need a different function here. I could easily write one down, but I'm not going to, because this is a bit of an aside. But we could write a different function which looked, for instance, like this. So this n dagger, we can call it, if you drop below n dagger, then this becomes negative. So then extinction is inevitable, because the population then starts falling of its own accord. Okay, because they can't find mates. And of course we see this in nature, that some species are doomed. When the numbers fall too low, they're doomed. Okay. And in that case, but the hunting, there's still quite a number of individuals around here to be hunted, yeah. Remember in the graph before, the numbers of megafauna drop pretty low. If the threshold for extinction is here, you could cross it, and then, oh no, we screwed up. Yeah, we crossed the threshold, the tipping point. So this is obviously the tipping point. We crossed it, we didn't know. Now we see they're all just disappearing even though we stopped hunting them. Okay. When we don't know where these thresholds are, if this is real, then this is a really strong argument for like being super careful. So that's why environmentalists love these tipping point models and these tipping point arguments. Okay. Enough on tipping points for now. Because what I'm going to do now is develop a completely different model without any tipping points. But one that is, we definitely know is highly relevant in many cases. Okay, I'm a bit of a skeptic about tipping points. We can talk about that. It's not like I'm saying there's no tipping points ever. I just think it's something people latch onto a bit too eagerly to try to get the results they're after. Okay, what we do is we add something else that the humans can eat. Okay, we add something else that they can eat, and then of course when the megafauna start running out, they can still survive and they can carry on hunting. Okay, then you could push the megafauna to extinction. So it's kind of the less dependent you are on the megafauna, the more likely you are to drive them to extinction. Yeah, if you're totally dependent on them, you're probably not going to drive them to extinction, unless there's tipping points. But if they're like, oh, a bit more take it or leave it, we love them, but, you know, delicious, but if they're gone, we can eat something else, even though it's not that you're thinking, therefore we can hunt them to extinction, even though you're just irrationally sort of just hunting and not planning, you can be more likely to drive them to extinction. So let's see how we can model that. How are we doing for time? Yeah, fine. So what we do in this model is we add small animals. And the basic idea here is the hunt, it's super simple, they're still just hunting, it's the only activity. Sometimes you find small animals, sometimes you find megafauna. Okay, so you stick out, sorry, I'm mixing languages here. What do you say in English? You go out hunting, whatever. You go out hunting, you might find small animals, you might find megafauna. And obviously depending on the relative populations, the chances, the rates of killing of the two types are going to change, yeah. So that's the basic idea. So now, y, instead of phi ln, it's L, which is your total labour. You go out hunting and you find phi n plus phi ss. That's your total catch, or whatever you would call it. And we've still got this equation for the human population and this equation for the megafauna. But in addition now we need an equation for the small animals. And to keep things simple, we say, look, the small animals, they breed very fast, their numbers basically adapt instantly to the hunting pressure, which makes the model a little bit simpler. So we say that S is S star, where S star is the carrying capacity, minus phi S SL. So if the carrying capacity is 1,000 of these animals in the area, let's say we're on an island, whatever, normally there'll be 1,000 of them, we're catching 100 a year, then there'll be 900. Okay, so it's super simple, yeah. Okay, so we've got S's here and here, right? So we can rearrange and say, shift that around, and we have that S is S star over 1 plus phi L, isn't it? S should be S star over 1 plus phi times L. Is that right? Yeah. Phi S. times L. Oh, but then we've got this equation, so we can stick this in instead of the S, and we can say that, well then y is L phi n plus phi s star over 1 plus phi s L. Put a square bracket there to make it clearer what's going on. Doke. And we've got, so yeah, this has changed a bit, hasn't it? Because I substitute before, what do we have here before? I can't remember. Phi n, which was y, yeah, we had y over L, consumption per person. And we still got y over L here, but now y over L is this square bracketed term, isn't it? Which I'm going to call square bracket dot. Okay, so now we've got this, where the square bracket is this. Okay, and we still got this. And again, there's no optimization or anything going on, we're just assuming the humans they go out and they hunt for all their worth. So again, it's super simple. And basically we can just simulate this. But this time I'm going to actually take you through some analytical stuff, because in the other model you're never going to get, however you choose parameters and so on, it's always going to look more or less the same. You're going to get these oscillations, you're never going to get extinction. In this model, depending on parameters, completely different things are going to happen in the long run. And we're going to have a look at this now. So I'm just going to pause the video and have a think exactly how I want to present this. Okay, so what we want to do here is work out, like, could there ever be extinction here? And basically, you're never going to literally get extinction in this model, in the model. All you're going to get is n approaching 0 in the worst case. Okay, because as n gets small, as long as L is finite, the harvest rate is going to approach 0, yeah. If n approaches 0, the rate of harvest of these animals is going to approach 0. So you're never going to catch the last one, I say. But you can drive asymptotically, the population can approach 0. So, but it could always bounce back in the model, okay. So the question is, when will the parameters lead to the n asymptotically approaching 0? Well, if that's going to happen, it must be that when n approaches 0, the human population doesn't, okay? Which must mean, and if n is approaching 0, the humans are harvesting effectively 0 of the megafauna, so they must be living entirely on the small animals. So it must be that humans can survive entirely on the small animals. But can they? Let's find out. To find out whether they can or not, let's just set n equal to 0. Okay. Then we have y is L phi s. So then, so let's see, y is L phi s, y over L is phi s, and s is this still applies, doesn't it? Yeah, there's nothing's changed to affect this, there's no n's or anything in this, so it's phi s star divided by 1 plus phi s L. That's y over L. Okay. I'm going to look at a crib sheet here. Right. And then we had, this is the equation for the human population, isn't it? Where this was y over L. But now, instead of the square brackets, we've got this, haven't we? So let's stick that in here instead. It's phi s star. Don't know if you can see this, never mind. Phi s star over 1 plus phi s L. Okay. Yeah, that's looking good. Now, can we sustain a human population? So this is the growth rate, or this is growth, not the growth rate. If we divide by LT, we've got the growth rate of human population as a function of, yeah, given that n is 0. Okay. And we're basically, that's LT, isn't it? We're interested in the case when the human population is stable. It's like, okay, does there exist a stable non-zero human population? Well, let's assume that such a population does exist. What can we say in that case? We can say that if we're at the stable long run level, then that level is such that, well, then these two are the same, right? Because we're at the stable level, so LT plus 1 is the same as LT. So this is 0. And we said it's a non-zero population, so this isn't 0, and this isn't 0. But this is 0. So this must be 0, which means that y bar equals this. So we're back here, and basically, I'm cutting corners here to save ink. We end up with that, right? Y bar equals phi s star over 1 plus phi s LT. Or L, where L now is the sort of steady state. We could call it LSS if you want it. These other things are all parameters. So we've got an equation with one variable in it, or one unknown, LSS, the steady state human population in the absence of megafauna. Sure. Okay, so then we multiply by 1 plus phi s LSS and divide by y bar. Take the 1 over and divide by phi s. We're going to end up with LSS equals phi s s star over y bar minus 1 over phi s. So once we've divided by phi s, that goes away and we have minus 1 over phi s. Which is cool because is this always positive? Is it always above 0? No. If phi s is too small compared to s star over y bar, then this will be negative, so which means there will be no steady state. There will be no stable population. So I hope you can see down here. I think it's alright, isn't it? Yeah. I can't stretch down here, but whatever. If phi s s star is less than y bar, if that, then LSS equals 0, so to speak. So what does this tell us? It tells us that if phi s s star is less than y bar, then as n approaches 0, humans will die out because they can't survive only on the small animals, which means humans will start to die out, which will mean that the megafauna will bounce back. Okay. So the point is, if we've got an alternative source of food that is we can survive on without the megafauna, then we can end up driving the megafauna to extinction. But if we're actually dependent on them to survive, we won't. Okay, so this is a kind of very optimistic conclusion from this setup. And of course you could criticize this. I've sort of been said, well, I'm skeptical about the tipping point models. You can be very skeptical about this. This is sort of saying that, look, this is built in sort of feedback mechanisms that mean that if we're kind of screwing up, then we find out before it's too late, or we're even forced to adapt before it's too late. Page or slide 15, we see what happens in two different parameterizations. Yeah, we have a very long. In the top one, there's no extinction, but we do have the way I've set it up, we have a very long period of very low numbers of megafauna, but eventually they come back. In the second one, they don't. Okay, so these the Malthusian models are not very relevant to modern economies. Why not? I'm just wondering whether to talk about this or whether we'll save that. I think we'll save that for Zoom as well. What kind of models are relevant? Well, of course, I mean, one thing we can say, it's super important, so I think I'll say this. I mean, basically, in the vast majority of countries, the population growth rate is no longer constrained by the availability of food. In fact, it's almost like the opposite. In the richer countries where there's lots of food, people have moved to the cities. There's hardly any population growth rate. We're living a modern life with availability of contraceptives and so on. It's actually in the countries often with the least I'm struggling to find the words in English, but the least sort of safe, secure access to food where the population growth rates are actually highest. So it's almost the opposite. Okay. And I think that was the last slide. So that's it on chapter 2, Malthusian growth. And that's me done for this evening. And it's Monday evening, tomorrow is Tuesday, and first time we actually meet. So I'm looking forward to that. See you soon.